Hello everyone, it's September 6th. Let's do this. Linked list in binary tree. Given a binary tree and a linked list with head, return true if all the elements in the linked list starting from the head correspond to some downward path connected in the binary tree. Otherwise, return false. So basically, is unique? Not necessarily. But it's fine. So given a root of the linked list, now root of the tree and the linked list with head, return true if all the elements in the linked list starting from the head corresponding to some downward path. A downward path means a path that starts from some node and goes downwards. So what I can do is, I can get like the path. I can get its path. Whenever the path comes out, we compare the two. But how do you know they are, well, I mean, if the values are the same, right? If the values are the same. Yeah, so you just need to check if this list, this array of numbers is a subarray of this. How do we check if one is a subarray of the other? I mean, we can go the path, one by one. Once we meet, and then we check both. When it's not, we reset. Okay, so yeah, we have some idea. All right, let's see how we're gonna do this. Okay, now I can do this. Check path. And we can call list values. This is a path. If is subarray list vowels path. True. Is subarray. Small, big. Okay. If small dot size larger than big dot size, false. Okay, otherwise index, I can call it J. If big dot get I equal to small dot get J, we can say J plus plus. If J is equal to small dot size, turn true, right? We matched. Else, if something doesn't match, match, it doesn't match. Oh, shoot. Yeah. You can't do it that way if you want to match the two. You say I can start matching and then at a certain point a mismatch. I remember there is a faster way to check if one, yeah, the substring, right? It's a faster algorithm to do substring. Is that the KLM, right? It's basically KLM. It's KLM. I am not going to do KLM on this. But regardless, this is not right. I have to... Yeah, this is not gonna work. This is not gonna work. We have to go from each one. I say J equal to 0, right? While J is smaller than small dot size, and small dot get J is equal to big dot get I. Ooh wee. All right, K equal to J, K equal to I. K, right? If they're the same, then J plus plus. I can do I plus J, right? And then J plus plus. There we go. Right? And then just keep moving. J smaller than and I plus J smaller than big dot size. And okay, when I get out, we say if J is equal to small dot size. Now we exhaust entire J, then we return true. Otherwise, we go again, and at the end we'll return false. Right, so this is subarray. If it's subarray, return true. Otherwise, return this. Okay, next what? Next is node is not null. Then what we're gonna do is it's basically just a path, right? Basically, it's just path. we are going to say path dot add node.val, right? And then we're going to say check path node.left, and basically we do exactly the same, but this time node.right. We go left, right, and at the end dot remove path.size -1. Actually, I can say if this is true, because one of them is true is sufficient. Now we just return true, right? If yep, I see. So if this or this, right, one of them is true, we return true. Otherwise, we do this and then we return false. Right, so this is a check path. And for here, I can just say return check path. No. Root list of our path. I mean, I don't even need the path. So path can actually be new array list, right? Yeah, the previous thing has to say list integer list vowels. Alright, and now we say list node equal to head while node is not equal to null. List vowels dot add node dot val and node equal to node dot next. Okay, then we do this. All right, let's take a look. This makes sense. Okay, let's put everybody in. All right, looks about right. $13.67. First, get the list of vowels from linked list. Then DFS root and check whether the linked list of vowels is a subarray of a path in the tree. Now, the implementation of subarray check is naive in this solution, which takes OMN time. There is a better way called, I think it's called KLM substring algorithm. KMP. My bad, it's called KMP. So very convoluted. I remember I was able to do it before, but no longer. There's a KMP. You need to compute the LPS array, and then and this is to check for pattern. Yes, it's for pattern matching. It's for pattern matching. For pattern matching, it's running what, m plus n, right? Yep, m plus n. Yeah, KMP. This is a KMP. Better way called KMP. That can check subarray. To be frank, KMP is used for substring matching, but we can use it here for checking subarray, right? Check subarray in OM plus N. However, I am not going to implement KMP. Too complicated. And I'm very sure, even if I implement it, I will never be able to memorize it. I kind of know, like in general, what it means, the KMP. I mean, in general, it's just we reuse. Now, whatever you have matched already, we can reuse that part for future matching, so we don't have to go back to the front every single time. Yeah, it'll work, but maybe they have the KMP and then it will be faster. I mean, if they have a KMP written in Java, they do have KMP written in Java. Array list. Nah, they have LPS in. Yeah, I remember I was able to solve this before, to write KMP before, but not gonna do it. DFS m times n, early stopping n times n, iterative approach n times n, KMP. Yeah, I know there's gonna be KMP. Nah, that's not happening, doing KMP. Where is KMP? Oh, it's actually not that complicated. Or you adjust the idea behind KMP. Reduce and optimize the approach. Okay, this is different. This is different. It's not KMP exactly, but it's like something similar to KMP. Well, we know the gist of KMP, which is to reduce repeated matching, right? So we said we can adjust this idea. Maybe we start matching. Maybe what we can do is, because we're traversing the tree, right? And then this is the linked list. Maybe if they match, when we pass on to the next one, we'll pass the next node to it. If they match, we'll pass the next node to it. If any node that does not match, we will check back to the front. So something like this. You do want to try, right? I know it, you want to try. It's I think it'll be a neat idea. Why not? Why not try it? Maybe we have this in us. Don't we? Don't we believe it? Yeah. And my attempt to use KMP-ish idea to solve this faster. So we will pass the next possible matching list node, right, to the DFS process. Right, if there is still a match, we keep passing the next list node. If not, we revert back to match the head. So basically, private boolean is subarray solve. We'll have list node, L node, tree node, T node, and list node head. Right? So basically we say if L node equal to null, return true. We matched all linked list, right? Otherwise, if T node is equal to null, return false. Right? T node is tree is over, but linked list is not over, so return false. Now both still exists. Then we say if L node dot val is equal to T node dot val. Well, we can say option 1, match from start. Well, we no. If the 2 is equal, then we say if solve L node dot next, T node dot left head. Right? Or solve L node dot next, T node dot right, return true. Any of those will return true, right? And if it's not true, then we shall return if L node dot linked list head dot val is equal to T node dot val. Oh, I can just return this. I can say return this. We can do early stop. So it's the same thing. Right? It's the same thing. But instead of L node on next, it'll be head on next. Head on next. So basically, if we match the current one, then we keep going. Right? If we don't match the current one, right? If we don't match the current one, then this is not KLM. This is not KMP. This is still OM times thing because we still have to go back to the front. But I don't know. It's kind of KMP-ish. Yeah, because the current one doesn't match, right? Then when you know the previous and this part, what's this part match the front? So we can move there. Yeah, this is not this approach uses a little bit inspiration from KMP, but it is not exactly KMP. So I expect it to be faster than solution 1, but in the worst case, its complexity should still be OMN. That's what I think. So if I say return solve head root head, that works. Nope. Pretty bad. The first one just failed. Oh yeah, also it might not be equal. Then we should still move on. Yeah, if it's equal, we do this. If it's equal, we do this. If nothing is equal, so the current node is not equal to, and then the head is also not equal to, then we shall just do dot next. Well, actually not, we're just putting a head. Yeah. Any faster? Oh no. That's my timeout. Yeah, everyone is. Yeah, that's not working. All right, I don't know. I don't know what they use for KMP. A prefix table. Yeah. Yes. Yes. The longest prefix, which means the prefix of the linked list, it's also a suffix of the path. Ah, the prefix table, I remember. Yeah. Yeah, because it's a suffix. And now we know this, now we can just go with this. So the prefix table basically is how long is prefix is matching in the suffix. Suffix ending at this. Right? How much prefix is matching here, right? So if we know that, then as we start matching, when we match some part of it, right? And then the next one mismatch. So the previous one, you can see how much prefix is matching up into this one, not how much prefix is matching. So now when you match the next one, you can match. All right. I don't want to keep doing this today. I'll have to read this KMP tomorrow. Interesting, yeah. I do want to. I said I don't want to do KMP on this one. I guess I lied. I do think it will be helpful if we go through KMP again. Alright, I'll go through KMP some other time.